So no, it's not there. Where the hell is... So I think variance stabilization method comes somewhere here. Convergence instruction to transformation. Not sure, it was somewhere here, I remember. Anyway, let me just write it into some. So suppose X is the number of success n out of n. So we know X follow binomial n comma p, n is known. So S equal to X by n is my p hat, is an estimator for p. Okay, that we do know. Now, for large n, we know that p hat follow approximately normal with mean as p, variance as p into 1 minus p by n. That is by central limit theorem approximately. Okay. Now, if you want to do a testing of hypothesis, you want to use p hat as your test statistic. So test, suppose your null hypothesis is something is p equal to say 0.5 versus some alternative. So under null, you can do that. But if you probably still you can do the testing of hypothesis, a p not equal to 5, say suppose a p greater than 0.5. Probably you will be able to run the test, but because under null, what you will do, you will say my test statistics set follow p p hat minus 0.5 divided by square root of basically 0.5 times 1 minus 0.5 divided by n, whatever n is, say 50 or 60 or 100, and you will do the test statistics. You will do the test, but can you do the power of, if you want to calculate power, you will not be able to do that. Can you tell me why? Because if you want to do test, check the power, what will happen? The power involves this, actual power will comes like this. Or if you want to say confidence interval, say confidence interval, even classic. Your confidence interval will be p hat plus minus, say some, if you want to do 95% confidence interval, it will be 1.96 times square root of p into 1 minus p by n. Now this p is unknown to you. So that means your standard error involves an unknown parameter, the unknown target parameter, for which you want to create a confidence interval. You want to say my confidence interval is say 0.35 to 0.4948 or something like that. You want to say something like that, or 5 to something like that. Okay, 5.3, something like that. But you can't say, because your confidence interval itself, your standard error itself is now involving the unknown parameter p. So you have to make an educated guess p. And that's create a logical error, because we want to make an educated guess of the range. In order to make the range, you have to make an educated guess of the p. I mean, it's like really weird thing. Do you understand the problem?
So a lot of the times we just substitute p hat for p without any logical
Correct,
explanation.
but that is a weird ad hoc behavior, right?
Yeah,
Why it has to be p hat?
right.
In some places, they just say replace it by half. They said, okay, that is the most, because entropy is the maximum in there. That means the most variability will find that p equal to half. Okay, चलो उसको उसमें से replace कर दो.
Mm.
So, in order to solve this problem, they got into this variance, something called variance stabilizing technique. What is variance stabilizing technique? So my target parameter is p, correct? But instead of trying to come up with p, if I can, so, and I know my p follow this one, this distribution. So p hat follow this distribution. If I can come up with a function g on p hat, g is a one-to-one function, which will follow normal g of p, but the variance will be a constant, preferably a known constant. then it solves my problem. Do you understand what I'm trying to say?
Yes,
Understand?
sir.
This is, so that is why it's called variance stabilizing technique. The question is, how can I do that?
Mm.
Any idea?
Sir, if mean is so one way would be to invert like that equation of P star into 1 minus P by N
It's not P star,
equal
it's
to
just P dot.
P into so take it as equal to a constant and then just reverse the value.
Say it again.
Create an inverse. So we have our normal distributions mean going as directly to G of P. So we have some ideas about which functions do that. That is one thing. The next
Correct.
thing is one is the linear set of functions. I don't know about other functions that do it. And
Right.
next, if we can find a linear function which, if we take the variance as constant and take the inverse function and
Okay.
try that.
Okay. Any other? Saraj, you said you studied this. So how did you solve this?
Uh,
Sir, some of the transformations that were told just now, was it for this reason? Like for normal and...
Yeah, but those
Yeah,
are the solution. Those are the solution. What Swaraj was saying, it was those were solution. But my
those are
point is,
the, yeah.
but how did you reach the solution?
So the idea is to come up with a transform statistic which has a constant variance, right?
Correct. So G,
So,
I have a P hat
right.
and I want to achieve a G of P hat. G is some one-to-one transformation or one-to-one function.
So that the B somehow cancels out, I think.
Somehow variance of that G P hat is constant.
Is constant. Like it will be independent of P.
It will be
So,
independent of P and somehow I can compute this constant. If I know the constant, my problem is solved. Because I know the G and I know the, if it is one-to-one function, I will be able to do the reverse it back to P hat, basically.
So we know how like the normal distribution transforms as a function. So basically we are transforming a normal distribution to some other normal distribution.
No.
So yeah, because P hat follows normal, right?
fine. But okay.
So we are
So
transforming
that
one
means the
normal.
transformation is some kind of linear. So
Yeah,
we will take a advantage of
exactly.
linearity. Okay, fine. That is to an extent right. To an extent right. We'll take the advantage of linearity. That
And
is actually true. But how we do that?
we know how variance from one normal transforms into another
How?
if we multiply or divide or add.
Correct.
So
Well,
then
that
we
is
can do the
fine.
inverse thing that I said, like
But how?
so for example, we have initial variance as P into 1 minus P by N. Let's say our final variance is some constant C, and on multiplying or dividing or adding to the distribution, we get a transformation function H for normal variances, right? Like if we multiply by, if we add something, there is no transform in the, so we can use this H to reverse calculate how to get C. For example, for the mean, the transform is simple. If you multiply by A, then the mean gets multiplied by. Similarly, you have some H function for the variance. So using that H, we can reverse calculate from the constant. I mean, that was what I was initially saying.
Okay.
Since it's a normal to normal transformation, and we know how normal to normal means change and variance is change.
Okay. Swaraj, can you remember?
I mean, I remember the transformation, but
Okay.
yeah,
What about Taylor series expansion? Does it ring the bell?
Taylor series expansion of what? The e to the power function. The normal.
G.
Oh.
Can I write it as G of, say, some P equal to P plus G dash P what else was there?
Divided by 1 factorial.
Yeah, that will be divided by 1 factorial or something.
Yeah.
And then
Second derivatives.
second derivative.
But
so it's x minus a. If it's x minus a, so g of x minus a, then the derivative is calculated at a
at x.
and it's multiplied by x. No. I think it's calculated at a and it's multiplied by x. Right?
So what is how I have
no,
to
then
change?
it will be calculated at minus a. Then you are taking it as minus a
No,
plus
I
x,
think
right?
like
Once, wait, I'll just check on the internet.
if it's x minus a, then you calculate it at a. Yeah, and you multiply it by x square, x cube, like that. So
Correct.
so if it's just g of p, then you're calculating it at 0 basically.
Correct.
So
Yeah,
g prime of 0, and it should be multiplied by p.
Yeah,
So
that's what I was saying. So if you are calculating at 0, then you get instead of p, you get 0.
0, exactly. So then the second term will be g prime 0 into p, but divided by 1 factorial, right?
Okay. Then
similarly, like p square g double prime of 0 by 2 factorial, if I remember correctly.
correct.
So g double prime p won't be whole square. It will just be like that.
Correct. Okay. Okay. Are you with me? Now, my target is basically what I want is, if I just say this is my p hat, this is p hat, this is p hat, this is p hat. Now take expectation of it.
The second derivative will also be at 0.
Yeah, the second derivative.
Yeah.
Now basically so expectation, I'm not very much worried. What I'm interested in is taking the variance. Now if I just say that p hat is square divided by 2 factorial, and then p hat cube by 3 factorial. These eventually will go to 0, and these higher order moments are finite. So I can approximate it to an extent, and then effectively my variance, so that I can, what they try to do, we can just approximate it with this relationship. Now you can see that this is a linear relationship. Okay, and if you take the variance of this and as a constant and then solve that, that will give you what transformation this G is. And that's how this sine inverse, I think, square root of P into 1 minus P, that what was for the binomial, what was the transformation? I think sine inverse
So
P.
sine
Inverse P. I think that's how they solve it and get the transformation. I remember, as far as I remember. Okay. Anyway, so this is the advantage is basically you come up with this, you create a confidence interval and then reverse back so that you get a confidence interval for P hat. So that's called variance stabilizing technique. Now you do it similarly, you can do it for Poisson lambdas, from normals, from the rank values, from the medians, and all these things actually can be done in the same way. So that is where these Z and M thing come. This is sort of a variance stabilization technique that they use for on inverse normal transformation. Anyway, okay. Now you're saying that here you got stuck and localizing convergence diagnostics, seeing the quality of quantiles, median absolute deviation, and small interval probabilities.
Can you also explain the folding thing? There are no references. They make some claims, but there are no references. I'm guessing it must be obvious or something. The one section just above this, the folding section.
Yeah.
Yeah.
Okay. The folded split. Okay.
So why is this working? I mean,
This
it
one?
wasn't not clear for the rank normalized either, but they've given references at least that we might just. There are no references either.
We call the rank normalized data measure computed values folded split or had this measure convergence in the bulk of the distribution to obtain a single conservative estimate. We propose to report the maximum of rank normalized split on this one. What? How they saying it? We call the rank normalized split or hat measure computed on xi mn values folded split or the measure convergence in tails rather than in bulk of the distribution. The single conservative R hat estimate equals to put the maximum of rank. Okay, you are saying the measure convergence in the tail rather than how the hell they come to this. That's what you are saying, right?
Yeah, I mean, they make this claim, right, to alleviate this problem, even above. So if you scroll up a little, there's a line.
But they're not saying that how the hell they got it. Okay.
Yeah.
That's a good point. That's definitely a good point. So both original and rank normally split or hat can be fooled if the chains have the same location but different scales. This can happen if one chain is stuck near the middle of the distribution. The delivery perspective we propose a rank normalized beta not only for the original draws beta NM, but also corresponding folded draws. Okay, this is something good point, Shahil. Definitely good point. Figure 1 demonstrates how our new version of that is some examples of lack of convergence are not detected by earlier versions. The potential scale reduction factor. We do not turn with this example to claim that our neighborhood is perfect, because it can be difficult to. Rather, we use these simple scenarios to develop attention about the problems of the traditional split and possible directions for the improvement. Okay.
So in their blog post, they mentioned something like this makes sure that it is sensitive to changes in scale. So is that obvious somehow and that I'm not aware of?
Which one is this new one? What they're proposing?
Yeah,
Changes.
so I pasted the blog post in chat.
Where is the blog post? Can you tell me?
Yeah, I pasted the blog post in the Zoom chat.
Okay.
There's like one line written about folding there, which is
Just a minute. Modeling. This is the one, right?
yeah, this is the one. I think this is normally Andrew Gelman's blog. If you
Correct.
scroll down around halfway down, there's this is a very accessibly written post. So, yeah, so here it says the point number 1 in the second one, folding the draws by there. So maybe that's very obvious and doesn't need justification. I'm not sure.
Some starring paper clips. Some string and paper clips. We came up with some truly terrible ideas, but eventually circled around the observation. Holding the draws by computing this and computing our hat on the folded chain will give statistic that is sensitive to change in scale. I think they're making an intuitive claim here. So they are saying that folding, if you fold the chain, by fold the chain, basically they are trying to say if you cut the chain into two halves, say if you have a chain of 10,000 rows, you take the first 5,000 and take the 5,001 to 10,000, these two things, and pretty much they may have converged. Okay.
So I think the folding metaphor might be the fact that they're using the modulus function. That's my guess.
Which one?
The reason that they're calling it folding is because of the
modular thing.
Modulus one, yeah.
Yeah. So,
and they're folding it about the median.
Correct.
How does
about
that
the median
say anything about the scale? I'm very confused by that.
No, they're saying that if there is any change in scale, that will be caught. Because M is the mth chain out of n thing out of n iteration. Each chain has a n iteration. So you got a median of the mth chain effectively, mth chain and nth fold, and you take the median deviation from the median, absolute deviation from the median, and if any one particular chain has higher scale is high, then what will happen? Then basically that median will be slightly deviated. No, what is theta nm? Wait a minute. I'm not talking. Theta nm is how they are estimating theta nm.
So theta nm, I think, is like of n is the chain, like the chain number, and
Chain
m
number.
is the observation number of that chain.
Right.
So I think they're just
And
simulating that, right? So it's like,
okay. No, is it a statistic of the chain or is it the just each value of the chain? I don't think it's a each value of the chain. What is theta nm here? That we have to first figure out. Okay.
It is the value of the chain, I think. So it is the NMH draw.
Sweeter statistics only for the original draws theta nm. Okay. So, okay. So imagine you have only two chain, m equal to 2, and one draw has one chain has standard deviation 2, another chain has a standard deviation 1. Now both chain has the same medians is 0. So that means one chain has a mean 0 standard deviation 1, another chain has a mean 0 standard deviation 2. Now you take the deviation of these chain of values minus the median. So the these deviation, absolute deviation, will be higher for the one which will have a scale, which has a standard deviation 2. This deviation on an average will be higher than the one. So that's why they're saying intuitively they're making this comment that I think it is.
And I guess one general question for me is
sensitive to change in skill. Yeah.
So as far as I know, the theory of stochastic processes is a very mature theory, right? And here it seems like it's a very, very ad hoc sort of, like they said, they just came up with some ideas and then tried to formalize it. So isn't it the case that we can like borrow some stuff from like just how people study Markov chains to figure out convergence? Like it seems like such a fundamental question that you would expect.
Yeah. Actually, Gelman always writes paper from very intuitive point of view. So these things he keeps doing these things. I mean, definitely we can use some of the stochastic process theories idea to formalize, make a suggestion that okay, this can be a little bit more formal way we can formulate these intuitive ideas. That will be nice actually if we can do that. Rank-based methods are robust against fat tails. So perhaps rank normalize the chain. Yes, we could the chain that is compute the rank for each draw inside the total pool. Putting these together, we get our new R-hat values after rank. So chains. The information we need to assess chain is full. what made me think that, he's suggesting instead of trace plot, we should look into the rank plots. This is actually, if this happens, this will be a major shift in the practice of MCMC.
Sir, so just one question, sir. Like we have read about how in certain cases, like quantile measures are preferred over moment measures, right? So,
Correct.
What I felt is like this paper is sort of exploring along those lines, like when moment
Correct.
measures don't make
Correct.
sense or don't work, like how some quantile measures can be incorporated to solve the issue. So, is that the crux of what is
effectively? That is my feeling also. Effectively, that is what they are saying.
Yeah, because they are like motivating us towards ranks and medians and other quantiles. So
Correct. And lot of asymptotic theory is already available for those which can be used to little bit formalize all these things.
Right.
Lot of asymptotic theory are already being available, so we can definitely use those results, because right now looks like this paper is written in a slightly intuitive ad hoc manner. I mean, typically Gelman's paper gives a lot of intuition. That is my experience. It's based on a lot of intuition. Yeah, so you see Monte Carlo estimates of the quantiles. Basically, that is what he's saying, that and actually it makes sense also, because effectively we don't know many times whether even the moments exist. Maybe the distribution is proper, posterior distribution is proper, but the high order moments exist or not, we don't even know. Correct. So if we don't even know high order moments exist or not, in that case, forcefully relying on moments based estimator is not a good idea. Rather, we should rely on rank based or the quantile based estimates. So in a sense, it tells us which are always much more robust, in a sense that as long as the distribution exists, they will exist no matter what. So that is what they're talking about here, effectively. So first example, they have taken variables are coming from Cauchy distribution with mean variance. This. Hierarchical. This is Gelman's favorite example, 8 school data set. Okay. And then he gave some supplementary material. Got it. Okay. I'm just stopping the record.